right? This is the idea. You see something people don't see. Right? Makes sense to you. Okay, today we'll just continue. This is the third lecture. And for the, first of all, it's a couple of, this is, today we're going to continue from last time, right? Last time we talked about sort of the analytical approach to understanding data distribution, right? Spatial linear models. We touch upon some of the basic concepts, but today we're going to dive a little bit more on the technical level, right? How to get the linear model, using linear models or mixture linear models to understand how to pursue low-dimensional structure in the data, right? Using them as some two classical examples, right? Probably you think you know everything, probably you don't. Probably you will find you probably know nothing about it, all right? So this is, hopefully the lecture will bring you to a different level. First, a few administrative matters for Hong Kong U students. The next lecture will be given by Professor Wang Peng, and he'll come here probably. And also he asked me, because he has to travel back and forth to Macau, I wonder if that we can have the lecture 1 hour early, or he has to cut short. He can only probably just teach a 2-hour lecture and cut it short. Or if you want to have a more extended 3-hour, 2.5 hours, we can start the lecture earlier. I don't know if that works for most. There's a lot of people involved. But if that's not, maybe we can do a vote. The TA can do a tally vote. If a mass majority is okay with we start the lecture by half hour or hour, and he can come here earlier, and so he can get back to, he has to teach another course in Macau. Because I'm traveling. If not, he can start with still 2 o'clock, but he ends the lecture a little bit early. Probably just, ends at 4 o'clock. Okay, good. Again, he will talk about, I'll mention what he will cover next time. And also homework 1 is assigned, is due in a couple of days. So basically it allows you to recap some of the things we talk about, right? Assign some homework about linear algebra, this Kalman filter, or all the different things, right? Least square extensions of linear least square, in my view, right? Linear models. Capture some linear algebra, a little bit of statistics, least square estimation, and so forth. And that's it. And also reading assignment for this week is start chapter 2. Okay? So that's the pace. For slate students, you joined this a little bit late, and there are already 2. And video recording of lecture 1 and 2 should be made available to you by now. And also homework, you should already start with homework 0, which is also reading assignment, and also homework 1. And I think I'll let the TAs coordinate what time it will be due, and for you. Again, reading assignment for this week, starting from this week, we will talk about the chapter 2 of the textbook, right? Guys, I think for many of you, maybe it comes as a little bit of surprise, right? There's lots of reading. Not the chapter 1, but also the appendix of some previous prerequisites. And you are a graduate student now. It's no longer undergraduate. Completely change your learning habit. Okay? You're learning this for yourself. You're not here to learn a degree. You learn the knowledge too. You have to catch up the pace, right? Do the reading on your own. But before you join the lectures, don't completely change your habit of learning, okay? If you used to, when you're an undergraduate student, you come to class, you learn something, go home, do some homework. Don't do that. Completely do the opposite. Get it prepared. Everything related to the subject, it's your responsibility to catch up, okay? I'm not going to wait for you. The world is not going to wait for you now, right? You have to learn to catch up. And it's your responsibility to learn. And everything I ask you to do, you should be capable of doing, okay? You don't know your potential yet, right? And catch up with the speed, right? So, and that's the administrative assignment. And also, so let's get back to continue from last lecture, right? So let's start with the whole course is we try to learn data lying on low-dimensional structures, right? We mentioned that in the past couple of lectures. And there's the analytic approach, there's the empirical approach. That's a chapter 1. Now let's start with the simplest class, right? The analytic model. We can model it, describe geometrically, algebraically, or statistically, right? This is our classical approach. We call it the analytic approach. the data is on a single low-dimensional subspace, right? Looks simple, right? Let's try to understand everything about the concept and the method, technical method about it. The problem is simple. If I give you a bunch of points lying around such a subspace, try to identify the base subspace, where that subspace is, right? From finite, possibly noisy data, right? Okay, simple, clear, right? So that's a question we start. Turns out this is one of the most fundamental problems, right? Almost everyone who is cool, you have learned from textbooks, right? Starting 300 years ago, nearly, right? Moscovich, Lerander, Gauss, Wiener, Kalman, Ben Logan, all this recent, right? Recited in the 1990s, the 2000 comprehensive. It's actually studied this. Right? Looks very simple. Try to have a data lies on low-dimensional subspace, linear model, it's just fit it. Right? Some noise models. So that's why all the assignment, appendix, right? Including my first book and second book, linear algebra, this is the most important part, right? Gets taught again and again. Class. You probably have learned many, many different versions. In mathematics, in signal processing, linear common filtering control, right? In signal processing, basis to last two, this is a statistics. This is a signal processing. This is a high dimensional data analysis, right? Compressive sensing. Everybody studies the same problem. Okay. And I think, in fact, everybody studies a simple version of this problem. Meaning that I already give you the subspace. How do you fit the data? Get rid of the noise. I already tell you what the linear structure is, the bases are. Try to fit it. That's the regression problem, right? So to regress the data, meaning that I already know to give you the subspace, give you the structure. Already tells you the dimension, even the basis for it. Fit the data. Okay? Actually, the problem can be harder, right? What if I don't know the subspace? Just give you the points. I don't give you analytic form. I don't tell you what the spaces are. The regressor, I don't give you the regressor. Right? How do I find that? Just from those finite points, potentially noisy. How do I find those data? For example, right? I only have endpoints lying on those subspaces, but I don't know what are subspaces. Right? How do you find those spaces? This is a classical question, already asked about 200 years ago, right? Pastrami and Jordan. Those are, if you learn mathematics, you know the name, right? Jordan form, Jordan this, Jordan that, right? Pastrami is also a famous phrase. Right? So he asked question: if I have a matrix, points like this, right? Form the matrix, each one is vector by matrix. How do I approximate them with the rank 1 outer product, right? Rank 1 matrix. Vertical, horizontal, right? That's a one factor. This is the second factor. Right. So this is already written matrix, as this is the simplest bilinear. This is actually called a tensor, right? Outer product is the simplest tensor form, right? TensorFlow, where it come from? Okay, now how do I find? Of course, I want to approximate this matrix with, let's say, here can be very high. N dimension could be n dimension. N can be millions. This could be 10,000, right? N is very large. But maybe I only have D is only 50. I only need a 50 dimension to fit this gigantic matrix. So this is actually the matrix. Basically, the intrinsic dimension is very low. It's only D. If I only approximate D factors, columns, right? 50 columns or rows to approximate such a humongous matrix. Approximate low rank matrix. What's the best solution? They already asked that question, right? I want to make this small, make this as close to this one as possible. How do I do that? It's called a classical matrix observation by rank 1 factors, right? Each of those factors is rank 1. I sum them together, it's up to rank 2, right? That's basic. Everybody got it? It's very simple. And of course, similar question you can call, this is the factor, but another one could be a slightly equivalent question, is that, can I just approximate this matrix? But I love this whole thing as a rank, I call it X. It's up to rank D, right? So find the X rank D, a matrix of rank D to approximate and minimize the difference. So this is actually equivalent. This question, as you can see, after about 100 years, right? This gets re-asked again. The important question always gets reinvented, re-asked. Okay, in a slightly equivalent different forms, right? 对吧？哪怕过了100年，还会被再问出来 ，right? So after it's the same. So as you can see, this is the pure algebraic formulation of the problem, right? I have a matrix. I want to approximate it with a low rank matrix. Remember when we talk about LoRa, deep networks? This is it. This is LoRa. Okay. So people will talk about this for 100 years now. Except that you apply this to the matrix for each layer. You approximate that to all the slow rank matrix to each layer, or the matrix you learn in the deep networks. Now, there's a so basically you can think about the classical fitting, right? This fitting is very geometric, right? I have noisy data lying on the subspace. I try to approximate all the data with project onto the subspace. That's it, right? This is pure geometric formulation, right? This is a pure algebraic formulation. There's a famous saying, right? Geometry is but drawing algebra. Algebra is written geometry. 所以代数和几何是个相辅相成，对吧？几何是画出来的代数，代数是写下来的几何。Right? It's actually equivalent. Now, there's also statistic formulation, right? Exactly the same problem, right? Statistics you care about if I have a random variable. If I have a random variable sample around, right? Sample around the low-dimensional Gaussian. Right? I have finite samples. How do I find that the major axis, the variance with the largest variation, or the second largest variation as well? So, basically, if statisticians want to fit a distribution, right, Gaussian distribution to the data, so right, so they have a statistical formulation. Right? Basically says you have a random variable y. I want to decompose him to find what's the most major component, second component, and so on up to D component, right? Sort of the axis of the Gaussian matrix, of the Gaussian variance matrix. Okay, so again, I try to find the basis support of this direction, and so on, right, up to D direction, such that the variable y can be approximated by this Gaussian, low-dimensional Gaussian. That's it. So this is purely statistical to minimize the variance, right? This is expectation since the distribution of y and so on. Right? You try to minimize this, minimize its expectation. The expectation is over y, and minimize it against the variables u and w. Right? Those two variables. Right? So this is actually pure statistical combination, again asked by the turns of the previous century, right? About 100 years. Again, see, the same question is asked from algebra of geometry. Gauss started, post-Gauss Gauss started, right? And then it's asked again by algebraitor about 150 years ago. And then 100 years ago, statistician asked again, right? So just like history, right? History is like this, right? Geometry is invented first, algebra, and then statistics, right? And then machine learning, right? So we're always doing that. We just recycle people's brain along the history. Right? So this is actually called a principal component analysis. So you can see this why this is important, this problem, fitting a linear subspace. Right? This is the only piece of results I know in my life, right? Has all been asked, has those geometric, algebraic, and the statistical interpretation. Okay? And the solution is unanimous, which is amazing, right? Both the geometric solution, algebraic solution, and statistical solution are exactly the same. You have never seen a result in mathematics like that. Okay? Never. Not yet. We'll see that later. So there may be a little bit explanation here. But so now how do we solve this problem then? What's the solution to this problem? Right? How do I find a solution to find the matrix, given matrix A, Y, right? I want to find the matrix X, which is ranked up to D. Y could be humongous, right? Huge matrix, millions by millions. But X is also million by million, but its rank is up to 50, let's say. Okay, that's the point. So the solution is given by this beautiful result called the singular value decomposition. Any matrix with rank R, all right, can be decomposed into the following form. You probably know this, some of you, right? This is orthogonal matrix. Basically, each columns, norm is 1, they're all mutually orthogonal to each other, right? This is also an orthogonal matrix. Each column is norm is 1 and also orthogonal to each other, right? Basically, UU transpose will be identical. VV transpose will be identical. Okay, very simple. And also the sigma is a diagonal or upper diagonal, lower diagonal, depends on the shape of the matrix. Could be rectangular. Okay, this is actually the form. This is called a compact form. If it's not compact, it could be a rectangular, So the geometry of this is very simple, right? I mean, this is the first, if you have the data, right? It's trying to fit in the low rank matrix, right? So first you just essentially change the basis, rotate your data, and then you rescale based on the axis aligned with each of the major axes. Once we scale, re-rotate. You also it's a rotation, right? So this is basically change of basis. Right? That's actually geometry behind this, the concatenation, the three operators. You rotate, scale, rotate again. Okay, so that's very much what those three things are doing. Acting on that basically decompose the action of A into 3 steps， 好吗？把这个任何一个线性矩阵表达这个线性变换，把它分解成3步 ，decompose into 3 steps. Each step is very simple. Each one just either rotation, scaling, and rotation. Okay, that's it. How to compute this then? Now we know this is a fact, right? But this is not a proof, right? How do you know this is true? But what is U, V, sigma, right? We need to how to compute it if this is important. Actually, computation is very simple, right? Everybody know, right? Eigenvalue decomposition, 对吧？奇子分不整这个特征子分解知道吧？对不对？Any real symmetric matrix 实的对称针，对不对？ They always have this decomposition. Right? You can always write down as the eigenvector, 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 right? So you can always decompose a real symmetric matrix as a orthogonal matrix. You see eigenvector is orthogonal, mutually orthogonal to each other, and there's R eigenvalues. So you have to compute it. I won't tell you how to compute that. We'll get this back to this, right? Suppose right now we take this for granted, okay? But computing eigenvalue is not a picnic either. Okay, we'll get back to this just in a second. Right? 假设我们已经能这个算出来了啊，假设这个算出来了，这玩意儿怎么算？这 guys, from now on, right? Whenever I say something, right? Give you say, always try to associate with price tag 对吧？这就是 computing thinking， 对吧？数学 thinking， 数学家不关心。 最后怎么算啊？只是概念，对吧 ？If it exists, the question is if I say something exists, your next question should always pop in your head is that how in the world I get it? Okay, what is the computation associated? Either give me a formula or give me a procedure so that I can find it. Okay, so for now, suppose I already give this to you. So then using this to derive the singular value is easy. Okay, how do I do? You sort out those eigenvalues, right, from large to right. Are all eigenvalues guaranteed to be real? 一个矩阵的 eigenvalue 都会是 real 的吗？不是，对不对？不一定，对不对？可能是负的，对吧？那这个为什么会是 real 的呢？ Are all symmetric matrix the eigenvalues supposed to be real symmetric matrix the eigenvalues is if the matrix is real symmetric， 现在所有的线性代数啊，现在看 quickly flashback， 对吧？你们学的线性代数，对不对？对吧？对称的实矩阵啊，它的 eigenvalue 是不是实的？是的，对不对 ？Guaranteed to be positive。你就写下来，不要 take for granted。为什么是大于等于0呢？什么情况大于等于 ？Positive semi-definite， 对不对？什么时候 positive semi-definite， 对吧？这个情况可以保证。如果任何一个对称阵，对吧？它是这个形式，它也就是 positive semi-definite， 所以它的所有的 eigenvalue 又是实的，又是正的，对吧？或者非零的啊，非负的，sorry。It's now negative, right? So all the things you have to flash back, okay? All the linear algebra that's why I asked you to read, okay? So once this is true, find all the eigenvectors. Now I can construct. I call sigma I to be the square root of lambda, and call ui as 1 over square normalized by a hit, using a to hit this v eigenvector again, right? Using a to hit the multiplied eigenvector, so that defines ui. Then it's your job to prove those so-constructed u1 to u are actually orthogonal。下去证明，好吧？这样啊，这样定义的，对吧？我就从 v 和 singular value 这样定义的 singular value 啊，来计算的 ui， 都是 ui actually not only their mutually orthogonal。第一，它们正交；第二，它们每个的长度是1啊，非常简单，大家去证一下，好吧？you know. But it turns out then you actually once you do this, you can rewrite this. A as you can actually show this is the truth. Right? A can be written down in this form. Right? This is a classical results. So hence, if you can compute this one, compute SVD, right? 这是一个对称阵，所以你看，这是 AG 阵可以是个方阵，对不对？是一个 rectangular， 任何斜阵啊都可以。So singular value composition is very how to compute. But I never tell you how to compute this thing, 对不对？特征值怎么算？对吧？哎，没有，我们没这黑板，这个有。Well, I don't know if you guys can see me online, but this is just right. We compute the delta lambda I minus A, right, equal to 0, right? This is the first thing probably pop up in your head, 对不对？对吧？行列4，对吧？用行列4去算。那么 this give you what? This give you a polynomial of degree n, 对不对？ In lambda. If this is n by n, this is going to be n dimension. But then you solve all the roots, 对不对？找根，对吧？多项式的根啊，就找到 lambda， 对不对？就是大家知道吧？啊，就是牛顿。待会儿我们还会回过头来，牛顿最早就是关于这个问题。OK， 牛顿为什么要找解啊？去解根，对吧？多项式的根。We want to find the roots of it. We'll talk about his algorithm. OK, his algorithm has the seeds for all the deep networks. OK， 所以 deep network is nothing new， 对吧？牛顿早就知道了。OK。All right, we'll get back to this in a second. Yeah. You solve the polynomial, right? 这是叫什么？特征多项式，对不对？一个矩阵的特征，大家应该学过吧？对吧 ？But solving this is humongous, right? There was up to 5 order. 为什么牛顿会发明牛顿算法 ？Why he invented the Newton algorithm? Because we know, right? Solving roots of polynomial, if it's higher than 5 degree, there's no formula 了，对吧？2次项有吧？2次项的根知道，3次项也有啊，甚至4有点绕，对吧？啊，世界的这个，尤其是 fourth order polynomial 跟是有解的，有必解的啊，但是有点绕啊，有点乱。但那个5次项呢，对吧？没有的，对不对？可以数学上证明的，对吧？对于5次方程，这个 polynomial equation 是没有必解的。OK，so you have to solve using what numerical solution。对吧？迭代，所以这是牛顿为什么会发明牛顿算法 ？OK， you want to find the roots of polynomials numerically, cannot just give up. You don't have right, give up the hope. So you don't have an analytic solution. You don't have closed form solution beyond the 5 degree. But remember, we want to compute this for a matrix of billions of dimensions, millions of dimensions. That's what the PCA does, right? That's what the PageRank does. 知道吗？ Google search PageRank is doing this SV. That's the PageRank story, right? 最早 Sergey 和那个 Brain, right? Larry Page, Sergey Brain, they were a graduate student at my Stanford. So they wrote a paper, submitted to the SIG-IR, Information Retrieval, the conference, the top conference in information retrieval. The title of the paper is called PageRank. Okay. And then the paper got rejected because the reviewer says, this is just SVD, this is a PCA, right? Why in the world is actually using this to compute the relationship between pages, websites, okay? It's actually exactly SVD. Got rejected. And those two guys said, well, then it's just why not we just start a company, implement that with that. to sort out the website. Okay, that's the story. So they quit. So the story tells what's up. 这个故事告诉我们什么 story，right？ 当然了，以后你的文章被拒的时候you know what to do If you truly believe your results, you know what to do, right? There's many other stories like this. We'll talk about that. Yeah. Anyway. How to compute? That's about it. Now you understand why Google still the other day right on the published Nature paper. Oh, we find the minimum way to compute the multiply two matrix. Right? 5×5 6×6的矩阵，用最少的计算量。Right? There was a Nature paper about this. Right? The optimized user reinforced learning to find a fewer operation to multiply 5×5, 6×6 matrix. That's still open problem, by the way. So they want to say, because they're computing matrix, anything related to matrix, if you can save 10%, 你们知道 Google burn 的电量the electricity Google burn is 1 or 2% of the entire electricity produced by the United States per year. So if you can help them save 10% of computing SVD, you will save them billions of dollars. Okay? 就这么简单So how important? So now what is the algorithm to compute the eigenvector, singular vector of A? 你们知道对不对？你看它的 singular vector actually is coming from this guy, right? The V is actually one of the part of the singular vector. V comes from the eigenvector of this matrix. So you have to compute the eigenvector for that one. So how do we compute the eigenvector for this one? Do you solve this? No, you don't. Okay, that's too expensive. Okay. Also conceptually you could, but that's right. Newton tried to do that. Right. The modern days, nobody does that. Everybody do this, right? So you start with the symmetrical matrix A transpose A, right? You start random vector, non-zero vector. You hit the random vector with n repeatedly, normalize. Linear transformation, normalize. Linear transformation, normalize. What this sounds like? Sounds like a deep networks, right? Hit with a linear operator, normalize. Linear operator, normalize, right? So, and also this will converge. Turns out this will precisely converge with the first singular vector you want. 它会收敛到这个方向上去Actually, geometrically fast. This is very efficient, very fast. You only have to do multiply matrix multiplication, multiply vector multiple times. And also this converge geometrically fast, which means that you only have to hit. Also, this convergence rate does not depend on the size of the matrix. Okay, no matter how big the matrix is, how big the dimension is, this converges geometrically, which means that it only takes about dozens of iterations converge precisely to that direction. It's a little bit magical, right? There's a very good reason for that. We'll talk about this. This is a fixed point algorithm, contraction map. So this is there's some fundamental reason. What this looks like? 我上次已经讲过的，跟上次讲过的 previous lecture, there's something very similar. You start with something random. Then what do? You shrink, right? You reduce. You get rid of something you don't like, right? Finally, converges to something clean, right? This is exactly you're staring at the denoising algorithm now. 所有的现在的生成的 AI 就是这个算法 ，OK, nothing else. 这就是一个 classic 的 denoising 算法 ，OK, except the distribution is simple, it's local, linear. Also, you pursue just a one-dimensional direction. 那我们把一个高斯，对不对 ？Start with random vector converge to the image. Image is very complicated, right? It's a surface on some tensor dimension. That's it. But conceptually, it's exactly the same thing. 所以不要认为现在的这个算法有多么的神奇，多么了不起。人类早就在做这个，都已经做的不做了，对吧 ？Only apply the same concept to something slightly different. Okay? This is denoising. Okay? This turns out to be the most efficient way to compute, much faster than an algebraic way. Okay? The other approach. 所以我们这要说的，我们这个书的开始第一句话 条条大路通罗马。All roads is Rome, right? But some are detour, some are slower, some are faster. So that's where computing comes. 对 ，OK， 数学是等价的，但是计算不等价，对不对？路不等价，对吧？数学家告诉你该做什么，但是并不告诉你怎么该做，对不对 ？Computer scientist, we figure out how to do it in the most efficient way. That's called compute. So now, once you know how to compute the singular value decomposition, then all this question become easy, right? Including this question, how to do the low rank matrix approximation. Once you compute the SVD of a matrix, once you know how to compute the SVD, then the finite, then I can write down any matrix, data matrix in this form. Then give me a D. This R could be, let's say, 500. If I want to approximate up to 50, the little d is 50, then I just have to order sigma. Remember, lambda is non-negative, 对不对？这个大小都是非负的，所以可以取根号也是有非负的，对不对？ Then I can order them. It's non-negative. I can order them from 大到小, from large to small, right? I order them and then cut it off at d equal to 50. Throw all the rest. Turns out you can actually prove this gives you the best optimal rank D approximation to Y. OK， 这就是 LoRa 啊，训练深度网络最后一步，对不对？训练完了以后，对每 for every layer you want to approximate the operator by a low rank matrix. This is what they do. OK, computer SVD, we keep the best D. Depends on how much memory, how much you want to cut. Right? This is how we compress a big neural networks as well, right? Each layer, the operator could be huge, matrix one. But then I can approximate the best top D, get rid of the rest. So saving this two are smaller, right? Rather to save a homogeneous matrix. Otherwise, see, I have to either save this homogeneous matrix. If I approximate with the scaling matrix, the multiplication, right, of two scaling matrix, that's a huge saving memory, 对不对？原来是7B 啊，可能现在就一个 B 就剩下了 ，right? So this is what they do. So whenever you do high dimensional space, what is this? How do I get rid of this? What do I do? Do you guys see this participant has request capturing for this meeting? How do I enable this? Anyone control? I have no idea how to. I don't know how to control this. So go to okay, yeah. Decline. It should enable. It's fine. Okay, doesn't matter. Well, you can enable and I don't know. So now, how do we do this? So everybody know how to do this now, right? You know the problem, how to approximate low dimensional subspace, how to compute it, right? Otherwise, the road is not complete, right? 所以一件事情啊，不光是问题重要很重要，代数、几何、统计 ，right? Very important. But mathematician tells you it's important. But computer science figure out what's the best way of doing. Okay? Otherwise, 到罗马的路是不通的。你知道罗马很好，你怎么去啊？哪条路最好 ？OK？ 要走牛顿的道路还是别人的道路 ？Right? It's very, very different. There's a very we'll get back to the algorithm in a second. Why we have to do this? Why this is a good idea? All right. Once we know how to do this, then now it's up to interpolate, right? I have data, right? I have a lot of sample. Once I compute the subspace, if I see a new data, I can project, I can compress, I can represent this in the subspace with only D coordinates, right? 我用不着记这么多了，对不对？这个点可能是 millions of dimensions, right? I need a million coordinates. But now if I know the UD, I can project onto the subspace. D is only 50. I only have to remember 50 coordinates to find where the point is, right? But of course I have to approximate. This point may not be perfect. I project out there's a little bit of error. That's called the noise. Against my model, you have some noise, right? I get rid of it. Those are noise I can. So this is exactly, once I have the subspace, I can do denoiser, I can compress your data. Right? So how do I do? If I give an arbitrary point, I head with the projection, project onto subspace, and lift it back to the original space, right? This is what you usually do. You find the x hat is exactly equal to multiply this x with this two operator, to x u transpose u, right? Consecutively. Now, what does this look like, right? This is already like a two-layer network, right? I hit with the first linear transformation and then with another one. So, right. We'll talk about it in the future. Why do you need this kind of revenue, right? Because in the deep network, usually those u and w are not normalized. Here, why do I do not have to add something nonlinear here? I don't have to normalize. Why? Because u star is already normalized. They are unitary matrix. Okay? You don't have to. Here, if you have a MLP, if it's an arbitrary matrix, the shape is very bad. So you have to reshape them. That's what the normalization is doing. We'll talk about that later. Now, so this is the linear model, right? Finding piece of data. Now let's be a little bit more general, slightly more general. Right? I have a bunch of data, and in certain spaces, right? We don't know the this classical story is that we know the data has some structure. You know, this is 声音信号, right? There's maybe some audio or some weird stock prices, right? So we're trying to process it, right? Again, this is very ancient story. People believe that our sound or the structure, data has some structure. Okay, especially start with sound, waves. Okay, we just look at the waves. Okay, they care about waves. The question is, we want to find a transformation. We believe that has some structure, right? Of course, in the original domain, it's very hard to find the structure, right? Then you apply a transformation, linear transformation, right? We hit with some linear transformation. Hopefully, after the transformation, the internal structure gets clear. Before the sound, right? If I transform to Fourier domain, 对不对？到频率，哎，这有趣了，对吧 ？Our sound are all band limited， 对不对？我们不会超过一定的 frequency，right？ Only 3K or something，right？ 所以所有的 radio it's about 40K or something，right？ Beyond that, it's all noise，right? There's no structure. So this is some very classical people believe. People believe this is a belief, faith. Okay, well, my data must have this kind of because the data are generated by strings, right? By vibration. By physics tells us, right? Those vibration, those sinusoids have structure, frequency are limited. Okay? The 共振频率不是 There's a physical reason to believe that your data may have some structure. So you apply a transformation, right? Then to reveal how the data was generated. 我们的 sounds were generated by composition of different frequency， 对不对？ So once in the frequency domain, that becomes clear。 就跟光谱一样，材料也是，对不对？材料千变万化，但一打光谱这个原子就那么几种，哎，对吧？你一看到它的这个 frequency 就那么几种，对不对？氢光谱原子就是这样。Right? So this is a fundamental. Once you do a proper transform your data to a proper domain, you actually see how it's composed of。 牛顿最大的贡献有一个，对吧？ 白光是七色，对不对？光谱分解Once you do the change the frequency, something 白的会变成 right? So this is how you apply a transformation to reveal how the data X actually tells you more about how Y is generated, right? What you saw Y is actually hidden by a D matrix. So the first most famous transformation, 对吧？ 傅立叶变换傅立叶的 story 也知道吧？是很励志的，对不对？也是 first proposal of an equilibrium. That's a different similar story, right? He's not quite a famous mathematician, but he believed, right? It's very intuitive. He proposed a Fourier transform, but not with a very strong theoretical justification. So people like Legendre or some of the 拉格朗日吧，应该是 I didn't believe it. It's just some heuristic thing, right? But turns out it's the most important thing in the world, right? So and everybody has to learn it. So Fourier transform. Right? You apply Fourier transform. Hey, why this doesn't work? This will show up. There's a delay. If you apply Fourier transform, right, to your data, right, suddenly in the frequency domain, you can see X actually has band limited frequencies, right? There's a lot of natural signal has a very clear characteristics in the frequency. Right? Our sound doesn't have any signal, right? even prompt people to develop the first image compression. Cosine, a discrete cosine transform is actually a discrete version of the Fourier transform, right? Even use it to meet image, right? For some, this makes a lot of sense, but turns out it's wrong to apply Fourier transform to images. Why? Fourier transform applied to signal. Well, if you in the frequency domain, if the frequency is band limited, right? Right. You can transform. You can say you can think about the signal is actually composed of finite number of low frequency signals, right? Composition, right? But the image is not. The image actually we want to share sharp edges, right? Sharp edges. It's band unlimited, 对不对 ？Step function， 那么大家做过复利变换，对不对 ？Step function the Fourier transform that the band limited goes on. Right? You want to keep those sharp edges, right? So it's not bad, but people use that anyway, right? That's why Jetpack looks a bit fuzzy. Okay, so people don't like it. Hence they, oh, there's something probably not very suitable for images. So they start looking for some other transformation. Also, it's a square matrix, right? Apply another kind instead of Fourier transform, can do some other transform, right? This, after how first ask this question, 提出了另外一种transformation, right? This is actually turns out that this transformation is very good for piecewise continuous signals. Piecewise, 就是这种节约的 continuity. This is also was a very big deal in signal processing. 火了大概好几十年，对吧？80年代80年代开始。People make assumption that your data are actually has sparse structure after the wavelet transfer. It's called wavelets 小波变换是另一类的正交函数、正交方程It's not a Fourier transform. It's another basis. Right? If you compress that, you get a better image compression. Right? So you can 看到一些 edge 保留下来。Some channels keep those edges. Right? So it turns out JPEG 2000最新的图像编辑就是用这个变化。The 效果要好很多 ，right? Much better. JPEG 2000最新的the new compression packets using wavelet. 现在大家在用什么？神经网络。We'll talk about that later. It's related. Google is using training neural networks, right, to do the compression, image compression. Claims to be better. Definitely, it's easy to beat the JPEG, right? Because this is just a fixed. So see, the point is that here the F or W wavelets, right? They're not learned, right? They're just start with the belief. Believe my data are frequency structure in frequency domain, or believe my data are generated by those piecewise continuous function. How do you know? How can you be so sure? Maybe the data has something else. Right? So this is the traditional approach, right? This is 数学以前 we make assumption, then we design what it is, right? This is the classical thinking about analytic approach. I start with some analytic assumption and then try to design a solution for it, find what's the best. Right? This is the traditional by design method, right? So then you obviously, just like Fourier transform applied to image, it's actually pretty bad, actually, right? But the people didn't know better, right? So a transform is not, such a transform not necessarily optimal for signal that do not satisfy the condition under which transform is defined. Okay? Remember, DCT is not ideal for image, but people use it for like 20 years anyway. So 你看这个现在有时候还是蛮草台班子大家讲别以为大家this is industrial standard, right? For 20 years must be gold, right? No, it's not. Something can be very stupid, very silly, actually, conceptually incorrect, but people just have to use it, right? Until they have their 2000. 你看2000年才改过来，很多年就知道不对，对不对？要过很长时间才改过来。那么改过来的 JPEG 2000也不是一定就最好，是吧？ So different kinds of signal, we need to design different transform, right? 所以即使是小波变换也有几十种，什么 curvelets, bandlets, rigidlets, right? So basically, they're all different orthogonal transformation, suitable for different class of signals. Right? Which one is the best? Nobody knows. They're all optimal under certain mathematical assumption about the class of signal generated. Okay? 但是 who knows? How do you know? 我就给你 bunch of image, which class it is? Nobody knows. You try, right? 所以这很奇怪 right? So now now you know why these days people try to learn from data driven. Then can we let data tell me what is the best transformation I should use to reveal its structure? 对吧？而不是像以前靠物理傅里叶，而是靠它的物理的 intuition，而且它也只适合，对吧？声音啊，类似于声音啊这样的物理生成的弦啊这样子，光谱啊，对吧？这样生成的信号，对不对？那其他信号呢？对吧？图像呢？对吧？股票呢？Nobody knows. So the question depends. This is a word learning. Can we actually learn the corresponding optimal transform from many samples? Then the data distribution tells us what is the transformation, what are the subspaces, what is the basis I should use. Tell me what basis. Right? For example, again, right? I have many data points. They're just columns of matrix, right? This is all I have. Can you find a dictionary, a basis transformation, right? It could be square. We start with could be rectangular, right? We'll talk about that later. But normally we assume this is the same. Okay， 简单一点，是一个正交，这就是一个方正啊，invertible linear transform. Okay, start with that special thing. So that X is very sparse. X has structure. 每个列变得非常稀疏。比如说 if it's a Fourier, if this is a sum, right? If I apply Fourier transform, then X will be just the first frequency, the rest is zero. Second frequency, the rest is zero, right? This is a sine, cosine, certain frequencies, right? So no other ones, right? All this X down zero focus on the first few low pass signals, okay? Low frequencies. 明白吗？ So but you have to find this one. The question is now this problem is a bit harder, right? So Fourier 变换告诉我 D 我已经知道了，小我也知道 W 给我知道嘛，对不对？所以给我 Y，give me Y，give me W，give me，then I can solve X， 对吧？这是线性方程，对吧？所以我只用做 inverse transform，apply the inverse of the Fourier transform，I get the frequency domain, right? But what if I don't know dx 我都不知道 ？I try to learn. Find the D such that X has the best structure, is most compressed, most clean. If you believe such X exists, if Y has such structure. 所以我们说过，对不对？我们这堂课的唯一的一个 inductive bias assumption is we believe my data has low-dimensional structure. Here, just assume Y has low-dimensional structure of this form. If I find such a linear transformation exists, such that X is very low-dimensional. OK？ 啊，你又问马老师，我为什么是线性的？我非线性怎么办？我们以后再考虑，好吧？现在我们先考虑线性。OK？More about that linearity later, right? So, but this is my belief. OK? If I believe there's a linear transform and such a low-dimensional structure exists, how do I find such a transformation through the Y? Y is always given here. 所以这就不是线性问题了啊 ，D, X are both unknown， 对不对 ？This is a bilinear problem. Okay. Okay, now let's look at this. Now I don't know X and Y, X and D. Now this is actually a little scary at the first sight. So computationally, optimizing a non-convex bilinear problem is generally NP hard. OK， 看起来很简单啊，就 X Y 对吧 ？D 和 X 乘起来，对不对？两个啊。Turns out that in general, this class of problem is actually NP hard. Right, especially when the dimension is high. 哎，看起来很简单，就来个句子。所以如果你了解多一点 the low rank matrix approximation, that classical setting there can be solved as really if you change a little bit, add any constraint, the problem becomes impossible. It's very special. The world is very strange, very interesting. Right? Only in that classical setting you have very efficient solution. You just change a little bit, the problem suddenly becomes intractable. The same here. In general, bilinear problem is going to be hard. Okay, this is another thing drives people crazy. In the beginning, people think they learn. So why they do Fourier? Why they do 小波? To design, assume the data is generated a certain way. Then derive what the optimal transformation is. 因为他们认为 learn 是不可能的。 There's actually a top mathematician, including Donald Dobishin, who actually is working on the top harmonic analysis people. They actually believe learning distribution, learning no-dimensional, learning such distribution is impossible. Even you can solve the problem. Even you can, even the solution, right? Even you can, even if I have algorithms, even this is not NP-hard, okay? Even solving the bilinear problem of this class is not NP-hard. But they believe this is just computational complexity, right? Solving the but this is sample complexity, meaning that how many points I need from those subspaces so that I be able to identify those spaces from. 大家想一想，如果我的 x 是 n dimension，x 可能有 k 个 k non-zeros，what's the possibilities？ 这个 x 可以在多少个子面上面 ？k dimensions。How many non-zeros？ x n 个坐标，对不对？其中有 k 个坐标是可以费零的。What is how many possibilities？ guys？ 组合数学不知道吗？数一数，能数清楚吗？啊 ，n choose k， 对不对？对吧？当 if n and k are large, how many possibilities? It grows exponentially, 对不对？所以你们可以看到 very strange, interesting thing, right? So even I can solve even the problem by linear problem is I can solve. I have some magic solver, some I can solve anybody. But the amount of data, at least intuitively, I need is at least n choose k, 对吧？哦，那些子，那就是 that's how many number of subspaces, k 的必须 subspace， 对吧？你概率上，你想你直觉告诉你，对吧？你每个子空间上面总得有一个点吧？还别说每个子空间是 k dimension, right? There's k dimensional subspace, right? I'm only asking this at least one point, right? In order to identify those, right? At least that's the intuition. Actually, that's the intuition behind all the top mathematicians for a while. They even write articles say, even if you can solve this problem you can never over-encounter. You need exponentially many samples, points on those structures in order to identify them. Turns out we'll see this is completely untrue. This is untrue either. 所以有时候啊，同学们，对不对？不要相信一些老大们的话 ，OK？ 所以过去20年 ，actually this is actually started with high dimensional statistics geometry. That's in the first 就2020的第一个10年啊，这个世纪 the first 10 years, right? A lot of old belief, opinion, right? Orthodox opinion, right? 甚至 authoritative opinion turns out to be completely untrue. 而且正好是反过来，哪怕是世界上最优秀的数学家 ，OK， 比我们这些所谓的工程师要严谨多的人啊，直觉比我们好得多的人，对不对？讲的话 turns out to be completely overthrown 啊，所以大家不要那么自以为啊，听到现在一些老大们讲的话 ，OK， 就认为当成那个圣典 ，OK，they are completely not true，OK，then maybe just their guess, the best guess，but their knowledge is very limited， right？ And also another problem from optimization point of view, right? So the solution to this entire thing is not even unique. Right? If you want to decompose y to d, right? This is the matrix. So we know we can stick a rotation or permutation between, right? Permutation, right? I can throw even p multiply p transpose is identity. It's also a solution. If you multiply them together, the identity 消掉，对不对？所以这个 solution 它不是 ，so permutation 不会改变 x 的 sparsity， 对吧？我就把这些列和向量、横向量、列向量交换一下 ，right？ Turns out this is not even the solution is not even unique。所以最早 people look at this problem, they immediately stop working on it. They say nothing rigorous, nothing guarantee you can say about it. The problems are too hard. The sample complexity can become combinatorial, right? exponential, and even you can solve it, there's many ambiguous solutions, right? It's a nightmare basically for optimization, right? Of course, the people say, well, the only thing you do some heuristics, right? 就是什么经验的算法。There's a few of them. People just try. If it works, works. If it doesn't work, nobody else can do. Okay, that's the situation for many years. So the question is, can we actually do this, right? Can we actually truly let's take why don't this is a good place to stop, right? So can we see something? Question here is, can we do something different? 所以这个课程希望给大家讲啊，就是最后讲算，这样我们 take a quick break 5分钟吧。但是呢，这样给大家讲，好吧？这是过去20年，对吧？颠覆了对很多过去的事情啊，我说大家，我对那些年轻的同学们，right？ Just two things are very important: stay curious, stay critical. Okay, two C's, and stay creative, three C's. Okay, curious, critical, and creative， 对不对？找到新的办法。这个课程可以给它告诉大家，你看通过 analytic 这个投实验是通过 analytic 方面来了解高维数据的统计和几个现象改变了我们整个对这个数据的很多认知。待会儿我会讲为什么完全颠覆掉这3件事情，turns out没有一件是对的 ，OK 没有一件是有 obstacle，turns out is a blessing 就完全是反过来，这件事是可以算，而且算的非常好，非常快，非常了不起。就是传统的这些，哪怕是纯数学，对吧？非常严谨的数学学科都会误解，大家很多误解，还别说后来，对不对？但后来当然后10年，对吧？第2个10年的 deep network， 因为大家从经验的角度也颠覆了很多认知，对不对？认为很难的问题，对吧？很难实现的、很难做的问题，就 actually magical。所以 this course is trying to see both from an analytic approach and from empirical approach, see what's really going on, right？很多不应该那么 mysterious， 实际上很多东西没有那么 mysterious， 只是以前我们的认知非常明确，而且很可能这些认知早就知道的不知道了，但是后面人都忘了，或者没有联系起来，没有意识到是跟我们早就知道的很多东西密切相关，甚至只是他们的一些 application， 就如此而已。所以希望通过这个课程呢，让大家了解一下这些东西，好吧？好，我们 take a 5 minutes break. Also for online people, we take a 5 minutes break and we will resume at 3:20. Okay, see you guys.